Hello everyone, and we are at our halfway of our virtual seminar series. So we have almost completed 3 presentations, and we are still yet to complete 4 more. The list is as in the screen. So we will start our first presentation after the break, that is at 1:30. ACI is an approved education provider for the American Institute of Architects and the International Code Council, and this webinar has been approved for 6 learning units. Please take note of our disclaimer on the screen for all the presentation in this virtual seminar series. So let's start with our today's fourth presentation, I would say. The title is Underwater Encapsulation with FRP Systems. And our speaker today is William Gold. Mr. Gold joined ACI in 2022 as a staff engineer. Prior to joining ACI, he worked in the construction chemicals industry for over 20 years. He brings a depth of experience in the use of fiber-reinforced polymer composite materials to reinforce concrete and masonry structure for both new construction and repair. Will has been an ACI member for many years and is a fellow of the institute. He is past chair of ACI Committee 440 on FRP reinforcement and currently serves as the secretary of both ACI Committee 440S and 440C, which are focused on the developing codes for the use of FRP in concrete. He is a registered professional engineer in the state of Ohio. So let's welcome Will and listen to his presentation. Welcome, Will.
Okay, great. Hello everyone, and it's my pleasure to join you today to talk a little bit about using FRP systems for repair of underwater structures. I'm glad that I could fill in for Dr. Sadamanesh, who unfortunately couldn't be with us today. He had an emergency that came up, but I do understand that he was slated to talk a little bit about repairing underwater structures with kind of a novel FRP system. I'm going to talk more just in general terms about the use of these systems for repairing underwater structures. I won't talk in specifics about what he was going to cover, but certainly want to give a little bit of an overview of where these systems have been used for repairing structures underwater and how they're utilized out in the field. Really what I want to do today is just kind of let you become familiar with these systems and how they can be used in underwater applications, understand a little bit about the components that are involved, and then we'll also talk about specifics around the FRP materials that are used, but also some of the grout materials that are used, which are go hand in hand with a lot of these types of systems, and then how they're actually erected in the field and placed in the field. So before I get into too much depth on the use of FRP, just to talk a little bit about underwater or marine structures, I think these are really fascinating structures in terms of the repair aspect. They are extremely challenging structures to repair. Anytime you're taking a structure and introducing the underwater nature of it, it really dramatically increases the complexity of repairs that need to be done. But certainly if you've been around structures in marine environments, you know that there are a lot of needs for repair out there. So the need is definitely there, and the challenges are certainly there. So it really makes for a really unique sort of approach to repairing these types of structures. So generally what we're talking about are things like submerged piles, submerged piers, oftentimes hydroelectric dams, offshore structures, seawalls, that type of thing. So all of these structures that are kind of in contact with waterways or with the sea or the ocean, these are always these types of structures that we're dealing with. And these are pretty challenging structures, or pretty challenging environments for the structures that are in those environments. If we're talking about structures that are on the coast that are in seawater or brackish water, these are very highly corrosive environments, a lot of available chlorides to support corrosion. We do have environments that are susceptible to rot if we're talking about something like a timber structure instead of repairing a concrete structure. And then you have oftentimes a lot of nasty organisms inside the seawater that attack concrete. There are certainly different types of marine organisms that can actually bore right through concrete, and in some cases even structural steel. I've certainly seen cases where some marine borers have gone through very high strength pre-stressed concrete piles, 10,000 psi concrete, and they bore through it and make it turn into Swiss cheese. So some very aggressive organisms that we sometimes have to deal with. And then there's also potential for damage from scour and abrasion due to wave action, debris in the water, those sorts of things. So it really is a pretty challenging environment for structures from a durability standpoint. And because of that, oftentimes these things do require repair and require that we go in and do something to rectify issues with them. So when we talk about repair, I often like to talk about how we approach this in terms of different repair zones. And if we're talking about a marine structure, there's really three major repair zones that we're dealing with. We deal with what I call the atmospheric zone, which is the zone that's above the water line that is never really below water. And in that zone, you can really do a lot of sort of traditional concrete repair and strengthening types of applications. We talked this morning about doing carbon fiber wraps and things of that nature. Those types of things are easily done in this more atmospheric zone. Then you also have the submerged zone. The submerged zone is the zone that is constantly submerged, that never sees the light of day, so to speak. And in that zone, there's not a lot of oxygen to support corrosion in a lot of cases. So in some cases, that's a relatively stable environment. But on the other hand, there can be things like organisms in the water that affect the concrete. There can be challenges from that standpoint. So those types of zones we have to certainly address at certain points along the way. But really the most challenging zone is that area in between, which is the splash zone. The splash zone is the zone, if we're talking about seawater, it might be the zone that's within the tidal range of the structures, so between low tide and high tide. But this zone is challenging because at times that structure may be exposed to air, at times it may be completely submerged. There is a lot of available oxygen to support things like corrosion, to support rot if we're talking about timber structures. There are still available organisms in that zone that can attack the existing structure. And there's also just a general scour and abrasion from wave action, from debris in the water. So there is a lot of potential impact in this zone as well. So this is really one of the more challenging one of the more challenging zones to deal with in these types of structures. So really looking at repair systems that can address the challenges of that splash zone is really pretty critical. And when we look at that zone, we're really focused on making sure that we have durable materials that we can use in that splash zone type repair application. We want to have materials that perform well, but yet we also have to have materials that can actually be placed in that environment. We are talking oftentimes about placing these materials underwater, so you've got to have materials that are specifically suited to be able to be placed in that environment. So there are a lot of very specific materials and technologies that are really driven towards addressing these underwater or near the splash zone type repair scenarios. I would certainly be remiss if I didn't mention that ACI does have a pretty comprehensive guideline on addressing a lot of the challenges of repairing underwater structures. That's the document that you see there, 546.2. This document covers a lot of ground and covers a lot of the approaches that can be used in repair of underwater structures. I'm going to touch on primarily the ones in that document that are focused on FRP materials, since that's certainly the topic of the seminar today. But there's other applications in there as well that might be of interest if you're dealing with these types of structures. So again, I'm going to focus more on some of the techniques that utilize FRP systems, and there's a few different varieties out there. But generally speaking, these kind of all follow the same sort of general approach. So I'm going to just talk a little bit about that general approach and how this is typically done. So let's take a typical case of an underwater pile supporting an above water structure, so supporting a wharf or a bridge or something of that nature. So if we have this structure and it's partially underwater, partially above water, the first thing that we really need to do in order to repair a structure like that is we need to do some type of surface preparation. So this is no different than if we're repairing something above the water line. You've got to do proper surface prep to make sure that you remove any of the damaged, deteriorated concrete, remove surface rust and scale off of the structure, and hopefully give the underlying structure some surface profile so that we can bond new repair materials to it. So we're going to have to do some type of surface prep on this particular structure. And if we're talking about above water, there's a lot of different available methods to do that. Grinding, abrasive blasting, water blasting, all of these types of things are available to us above the water line. But if we want to do surface prep below the water line, we have to start looking at some specific tools and methods to be able to do that. The two most common are either grinders that are pneumatic instead of obviously electrical. They're pneumatically operated tools that you can use underwater, or very high pressure water blasting that's done very close to the surface of the structure that you're trying to prep. Both of these methods have been used pretty successfully underwater. What you see there in the photo is a photo of a pneumatic grinder that's often used in prepping underwater structures. And then if you look at that tool in operation, looks something like this. So you're operating this underwater, removing, in this case, a lot of marine growth, rust, scale, that type of thing off the surface of the existing structure. Now, one thing to note about underwater structures is that it is often very critical that you do surface prep very close to the same time that you're doing other final repair applications. A lot of times the prep that you do to prepare the surface only lasts for a matter of maybe 24, 48 hours before there's new marine growth or there's new surface rust on the structure. So oftentimes there's very tight windows between actually prepping the surface and then executing the ultimate repair that's done. So in a lot of cases, you'll see specified windows between doing surface prep and then doing the actual repair application. Okay, so assuming that we can now get through the surface prep piece of this and then move on to installing a repair system, when we're talking about these FRP systems, they're really designed to more or less encapsulate the underwater structure. So again, there's a lot of different varieties of this, but generally what these entail is using the FRP material as essentially a stay-in-place form that goes around the concrete structure, and then that stay-in-place form is filled with a grout to encapsulate that underwater member, whatever it may be. So the jackets are, or these forms are FRP materials. They're preformed. Oftentimes they're custom built to match the overall shape of that structure. I'll show you some examples of that here towards the end. And they're designed to match the shape with a very slight, just slightly larger than that existing structure, so that you can fill that space between the jacket and the existing structure with some type of grout material. So the jackets are placed around the structure. Oops, sorry, that animation didn't work too well. But those jackets would be placed around the structure. They're usually prepped above the water with adhesives on the seams to bond the forms together as you place them around. The adhesives that are used are marine grade materials. Typically, they're designed to be used underwater and designed to cure underwater. So these are specialty types of usually epoxy adhesives that are used to do this. And then these are simply placed around an existing structure, as you see there, usually using divers, just depending on the application, depending on the depth that these things need to go. And then once the jackets are, these FRP jackets are in place, usually there's some type of temporary bracing that's installed. The bracing is there to hold the jackets in place while the grouting operation is done. The bracing prevents the jackets from bulging or deforming under the grouting pressures that are used, and just secures everything in place while the grouting operation is being completed. There's also, of course, some type of seal that we need to use, especially on the bottom of this encapsulation, so the grout doesn't flow out through the bottom of the member that we're trying to encapsulate. So there's usually some type of seal, usually with an adhesive like an epoxy or some type of foam seal that's used at the bottom of the encapsulation to seal it off. So here you see an example of an FRP jacket that's been installed along with some temporary bracing to help secure it in place. And then once that is all in place, we can then look at placing grout in that annular space between the FRP jacket and the existing structure. So I'll talk a little bit about some of the different grouts that are used. These are typically either a cementitious grout or an epoxy grout. The epoxy grouts, sometimes you'll see the resin and the hardener of the grout mixed separately, each of those components mixed separately with sand, and then they're pumped separately and actually mixed right before they are pumped into this encapsulation. So here's just a piece of equipment, piece of pumping equipment that's being used to mix and pump an epoxy grout. This pump, there's two separate hoppers. One hopper is for the resin with aggregate or sand, one's with hardener and sand. And again, those are mixed separately, pumped separately, and then mixed right before they enter the annular space between the jacket and the structure. So then as the grout is placed into the annulus, the grouts are designed to have enough density to displace any water that's entrapped between the FRP form and the existing structure. So as the grout is placed into that structure, they're placed from the bottom of the encapsulation, working their way up. And as they're placed in the bottom, they force water to rise to the top of the encapsulation, and then eventually that water is expunged out the top of the encapsulation as that grout is placed in. Just to note that I'm showing this grout being pumped. Pumping is not the only way to place the grout. I'll talk about some of the different placement methods, but generally speaking, you're trying to get the grout placed from the bottom, working your way up to the top of the encapsulation. So we keep then pumping grout until that entire FRP jacket is then filled with grout. That annular space is completely filled. And we have a good quality bonded encapsulation of that existing structure. So here you can see a photo. This is a photo of an encapsulation being completed. And one of the things to notice about this photo, in this case, the jackets that are being used are a glass fiber jacket, a GFRP or fiberglass jacket. The GFRP jackets are nice from the standpoint that they are opaque, or not, sorry, they are translucent, they're not opaque. They're translucent so you can see through the jacket to a certain extent. And if you look closely at that photo, you'll see kind of a darker shade just above the waterline, and then you'll see kind of a lightish gray shade of material just above the waterline. That darker shade is the water that's being forced out, and the lighter shade of gray is the grout as it's being pumped in. So you can actually visually monitor to a certain degree what's going on behind that jacket as the grout is being placed. You can monitor placement and make sure that things are being well consolidated, that voids are being filled, and that there's no large voids within that grout placement behind the FRP jacket. So allows you to end up with a very good sound repair that is fully encapsulated back behind that jacket. Then once the grout is fully placed, there's usually some type of watershed detail that's just hand placed on the top of the encapsulation to make sure that any water doesn't pond on the top of the encapsulation. And then the bracing, temporary bracing, can be removed, and then the encapsulation is complete. So this is kind of the general approach. And then what you're left with is a structure that's been repaired. We've repaired any spalled areas, any damaged areas of that structure that's being encapsulated. And then we've also provided a pretty robust protective layer around that existing structure. So we've used an FRP jacket that's going to provide a lot of protection to that underwater structure, protect it from additional marine growth, protect it from things like scour and abrasion, and also protect it in some cases from additional corrosion issues that might be going on. So, so these can be really beneficial, not only repair methods, but also protection methods that help really extend the longevity of these structures as they sit there today. So just a couple of things on the specifics. What I showed in the slides, these are all GFRP fiberglass jackets that have been used. These are by no means the only type of jacket or only style of jacket that can be used. Fiberglass jackets do have the benefit that they are relatively cost effective, and they are, as I mentioned before, translucent, so you can monitor the placement of grout, for example, behind the jackets. But generally speaking, even though fiberglass materials might have some structural capacity, usually these are not meant to be structural encapsulations. Usually these are just meant to be more or less protective. So they're not really adding much structural value other than maybe repairing some cross-section, reinstating some cross-section of a pile. But they're really not adding much in terms of structural capacity. There is the opportunity to use something like a carbon fiber jacket. I know that Dr. Sadamanesh was going to talk a little bit about the use of carbon fiber jackets. These can be used both as a protection element and as a structural element. So I know that in the morning, Dr. Al-Qadarji talked a lot about seismic retrofit and confining columns. You can do the same thing using carbon fiber jackets underwater to provide confinement. And these jackets can, in that case, be structural. I guess, downsides of carbon fiber jackets would be, number one, just the cost of the jacket itself, which would be quite a bit more than a fiberglass jacket. They would be opaque, so you would not be able to visually monitor grout placement, but they, again, can provide that additional structural capacity. The caveat there being that they would need to be fairly well bonded to the pile, so doing things like adequate surface prep and that type of thing, and then monitoring the bond strength would be critical in those types of applications as well. Then there are also jackets that incorporate some type of galvanic protection. So this is a photo that that you see there. This is a fiberglass jacket that has a zinc mesh on the inside of it. The zinc mesh is electrically tied to any steel element, so say reinforcing steel and a reinforced concrete element would be electrically tied to that reinforcing steel to provide galvanic protection to the steel. So the mesh would corrode sacrificially to the steel corroding, much like we do in a lot of other concrete repair applications where we use galvanic anodes to help mitigate corrosion. These can also be incorporated into these jackets to provide more robust corrosion protection. You can also use these types of systems in combination with bulk anodes, where you're tying chunks of zinc onto the existing structure, again, to provide some galvanic protection to the existing structure. That photo that you see there, that is a fiberglass jacket that has a zinc mesh on the interior of it. Very typical style of a galvanic type jacket that is used for both protection and that sacrificial component to provide corrosion protection as well. So just a couple of notes on the grouts. The grouts that are used, again, are generally either an epoxy grout or a cementitious grout. Epoxy grouts are, at least in my opinion, tend to be a little bit more durable because they do bond much better to the concrete substrate, and because they are impervious, they don't have a lot of issues with water and oxygen infiltration. So these epoxy grouts tend to be more durable, but they are certainly a lot more costly in terms of the material itself, and also in terms of placement, just because epoxies are a lot more difficult to mix and apply. They require special equipment. The equipment has to be cleaned frequently because of the nature of the material that you're dealing with. Also, epoxy grouts can have very high exothermic reactions, which means if you have a very large annular space between the jacket and the existing structure, if you're trying to encapsulate something that's, say, 0.5 meter thick, that high exothermic reaction is potentially going to cause issues with cracking of the grout, just because of the sheer mass of grout that you're trying to place. The other downside to epoxy grouts is that they cannot be used in conjunction with galvanic systems typically, and that's because these grouts are completely non-conductive, and galvanic systems do rely on some conductivity of the grout in order to properly function. So generally you won't see epoxy grouts used in the galvanic type systems. On the other end, cementitious grouts, these are generally lower cost materials, are a lot easier to mix using just conventional mixing equipment. They're a lot easier to apply. But again, they're lower in terms of bond strength, so there can be some durability issues. They may not have quite the life that an epoxy grout might, but if done properly, they can still result in a pretty quality concrete repair. I should also mention that they can be used for larger placements. They don't have quite the same exothermic reaction that epoxies do, so they are suitable when you're trying to do a larger depth repair. There's also a bullet point up there about the coefficient of thermal expansion, CTE. Epoxy grouts do have a CTE that can vary from the base concrete. So they do have to have some filler. Usually in the case of epoxy grouts, you're just talking about a sand as a filler. The fillers are used to help match the CTE more closely to the concrete. But again, the fillers need to be used in the proper ratio, and these can then become more difficult to mix in place. So there can be challenges with matching the coefficient of thermal expansion of the concrete itself. The last thing that I'll mention before I leave this slide is that, as with a lot of the other things that we've talked about today, these are generally systems. So you will see manufacturers that provide a system that includes the FRP materials and the grout materials. And usually these are designed to work in conjunction with each other. Certainly don't recommend just going off and buying some FRP forms and then filling it with a random grout. It is important that these things be matched and that the performance that there be some history with performance of the grout that's used along with the specific jacket that's being used. Okay, then in terms of grout placement, again, I showed grout being pumped, which is the best way to get grout placed with very good consolidation, very good grout penetration behind the annulus. Pumping, however, is relatively complicated. It does involve pumping equipment, usually requires divers that go down to actually attach grouting hoses and that type of thing to the jacket as it's being, as the grout is being placed. So it is much more complicated from that standpoint. There are applications where you can, instead of pumping the grout, you can trimmy the grout, which just means dropping a grout hose between the jacket and the existing structure, dropping a grout hose down to the bottom of the encapsulation, and then essentially pouring grout into the form from the bottom up, allowing gravity to kind of do its work and expunge the water out. Trimming the grout is a little less complicated, doesn't require as much horsepower out of the pumping equipment to get the job done. And in some cases can be done without divers, but you can have issues with consolidation of the grout or allowing water to still be entrapped in the encapsulation after the grout has been placed. So trimmy can be a little bit less, you can get less consolidation and less quality grout placement out of that type of method. Then there are also other methods. These are discussed in that 546.2 document. There are grouts that can be free fall placed, so you can actually drop the grout through water. The grouts are designed with anti-washout admixtures that allow them to fall through water without dispersing cement, and then force the water out. Those are generally used in more shallow placements. They're not used in very deep placements, but those types of materials are out there. And then there's also pre-placed aggregate placement methods where, especially if you're doing very large grout placements, you can pre-fill the forms with a coarse aggregate and then pump grout into that form with coarse aggregate and form more of a concrete encapsulation than just a grout encapsulation. And those again are good for very deep type placements where you're using a large quantity of material to fill an annular space between the FRP jacket and the existing structure. So this is just a photo. This is a photo, obviously, of a timber element. This is a timber pile that's been repaired by a pressure injected grout. And just want to emphasize the benefits of pressure injection is that you do get very good consolidation of the grout right down to the point that you actually can start more or less injecting small fissures or cracks in the existing structure. So you can see the larger cracks in that timber pile. They've actually been filled with the grout as it was pressure injected, into that pile. So with pressure injection, you do get very good consolidation and really, in some cases, very deep penetration of the grout into things like existing cracks and voids in that existing structure. Okay, so just a couple minutes more. I just wanted to show a couple of very quick case studies. The first one here is on the Noden Causeway that's up in Fort Frances, Ontario, just north of the border up in Canada. This particular structure, it's a very lengthy bridge that goes over the over Rainy Lake in Ontario, in the I guess it's the western part of Ontario. The bridge is part of the Trans-Canada Highway that runs all the way across Canada. And this particular bridge is supported on steel piles, and it's essentially steel cylinder piles that comprise the support structure of this bridge. And there's actually quite a number of them. There's over 1,100 steel piles that support this bridge as it spans over the lake. So very prominent bridge, very lengthy bridge over a beautiful area there in Western Canada, or Western Ontario. This is kind of a photo of the structure and some of the issues with it. This photo doesn't really do the amount of damage to the steel piles justice. There was quite a bit of damage to these steel piles that was really the result of microbial-induced corrosion. So there is an organism in the water that creates a corrosive environment for the steel, and that organism creates this environment that creates a lot of pitting corrosion on these steel piles. So you can kind of see that damage in the photo, but again, it doesn't really do it justice. There was quite a bit of pitting corrosion going on throughout all of the piles on this structure. That photo you see there is actually taken during the wintertime. You can see also in the pile in the background a lot of the ice buildup along the pile as well. Very deep sheets of ice that form on Rainy Lake in the wintertime. And actually a lot of original bridge construction was done by just driving piles with equipment that was driven out onto the ice. So they weren't even doing it on open water, they were just doing it on the open ice during the wintertime. So the repair of these structures involved in FRP encapsulation, but because of the severity of the pitting corrosion, there was a structural remediation as well. The structural remediation entailed putting basically high-strength steel rods and steel cages around the existing steel piles, along with some shear lugs that were driven into the face of the steel pile to create bond between the steel cage and the existing pile to allow some stress transfer between the steel cage and the existing pile. So you can see that in the photo there. There's that steel cage with periodic shear studs that are going through it. And then the gentleman back behind there is then installing a fiberglass jacket around that steel cage and those shear lugs. And then that ultimately gets filled with an epoxy grout, in this case, to fill that encapsulated pile. So you can see that in the photo there, some of the grout just coming up out of the top of that encapsulation. So a lot of these were originally done just in sort of that splash zone, which was about a 4-meter height of very severe pitting corrosion. Ultimately, a lot of these were encapsulated, though, full height. You can see some of the piles there on one of the major support elements of the bridge. So some of these were encapsulated at pretty large depths, going down to 20 meters, in some cases below the water line. So very large encapsulations in a lot of these cases on this particular project, but very large, very successful project that was completed back in about a little over 10 years ago and still functioning very well. So nice case study. Then the other project I'll show just before we wrap up is a little bit different application. This is on a hydroelectric dam. Just now realizing that both of these projects are up in Canada. No particular reason for that, but just two interesting projects up in Canada. This is the Deshmukh bridge up in Deep River, Ontario, just on the border between Ontario and Quebec. There's a number of hydroelectric dams that run along the Ottawa River there in Canada. This is one of them. It's about 20 kilometers north of Ottawa and supplies power to a pretty large area in Ontario. This structure, if you look at the downstream, what they call the tail race structure, this is where all of the water from the dam exits out the other side into the river. And this tail race structure was originally built back in the 1940s along with the rest of the dam and had quite a bit of damage due to scour and abrasion over the years. You can kind of see that in the photo there. If you look right at the water line, you'll see some of the damage to the concrete structure there at the water line. If you look a little bit closer, it looks like this. Some pretty severe loss of concrete section in a lot of these areas. There was up to 0.5 meter of concrete lost in some sections of this tail race structure, so pretty deep sections of concrete that were lost. And obviously you can see in the photo the steel reinforcement exposed in a lot of these cases as well. So really the challenge here was to go in and restore the section and repair and protect these areas. But because of the operation of the hydroelectric dam, they did not want to shut the dam down for very long. They actually had a requirement that the dam could only be shut down for 10 days, which really didn't allow for a lot of repair methods that would have required dewatering and building cofferdams and that type of thing to go in and do repairs. So really, because of the minimal shutdown time available, things needed to be done below the water line to execute all of these repairs. And at the same time, this is a protected water zone. So the Ottawa River did have a lot of requirements in terms of what could be put into the water. And there was a lot of environmental monitoring of any hazardous chemicals that might end up in the water stream itself. So the overall approach here that was taken was to use stay-in-place FRP forms, fiberglass forms that were placed around these damaged sections. And then the grout would be placed by pumping an epoxy grout into the bottom of the encapsulation. And then as that grout was pumped in, there was a vacuum system that was installed on the top of the encapsulation to remove any contaminated water, any water that was mixed with freshly mixed epoxy, so that there wasn't anything that ultimately ended up in the waterway. So this was meant to be a completely sealed sort of environmental approach to this repair. So this is some photos of that operation ongoing. This is obviously a multifaceted type of structure. It has a lot of reentrant corners and outside corners as well. So the entire thing is formed with these FRP forms around the exterior. And then grout is ultimately placed into these forms, and that contaminated, so to speak, water vacuumed out through the top. And then this is a photo after the grouting operation has been completed. A few core samples just showing very good consolidation and bond of the grout. And then we have the nice before and after photo. And then my favorite, the encapsulations actually with the facility in operation. And these encapsulations have now been in place for actually going on almost 20 years now. So very robust encapsulations that were installed. So with that, just wrap up. Just hopefully this gave you a little bit of a nice idea of how these types of systems can be used in this sort of specialty application of repairing underwater structures. And would just ask Aparna if there's any questions that have come up along the way.
Thank you, Will, for such an informative session. I think it included this encapsulation. I was hearing it for a first time from you. I have been hearing GFRP and other strengthening techniques for most of the time, but this was really different, a unique topic, and you did justice for the topic. I would say it was really nice to hear it. Thank you so much, Will.